What's up everyone, welcome back to another video. In this video we're going to be going over chapters 3 and 12, which is basically the least, square regression line, and chi-squared. So the first thing we're going to cover is chi-squared. Alright, so there's three types of tests when dealing with chi-squared. There's goodness of fit, independence, and homogeneity. And whenever you're trying to find your test statistic, which is chi-squared, using this formula. You're adding up all of the observed minus expected counts, squaring that, and dividing by your expected count. And we'll be doing examples so you can see how to do that. Alright, so the first thing, goodness of fit. So goodness of fit, you have one sample and one variable. Your null hypothesis is that all of the claimed distributions or proportions are correct. And the alternative is that everything, or at least one of them, is incorrect, or all of them are incorrect. Your plan, the naming is chi-square goodness of fit test. The conditions are random, independence, and large counts. Random is usually stated, independent, n has to be greater than 10n. Large counts, that's the new one. All of your expected counts has to be greater than 5. For the do, you use this formula to find your test statistic, or use your calculator. Conclude, you're basically either rejecting the null hypothesis and saying if you have convincing evidence or not convincing evidence. So here's an example. Keyword, you can read the question, but the keyword here is equally likely. And also, if you look in the chart, there's only one row with numbers. So those are two indicators that show you that tell you if it's goodness of fit. In context, the null hypothesis is that all the claimed distributions and proportions of bird visits are equally likely. We're using bird visits because that's just what the problem is talking about, so that's what it is in context. And then alternative is just the proportions, or at least one of them, are incorrect. Okay, so plan, I named it, all the conditions checked out. And so now for the do part. So for goodness of fit, the way you do this in the calculator is you want to go to stat edit and type in your observed and expected counts in L1 and L2. So in L1 you type in your observed counts, and in L2 you do expected. And so how do you find your expected? So in this problem, it says equally likely. So that means every single expected count has to be the same. And if there's 350 in total, and there's 4 different sections, 350 divided by 4 is 87.5. So the expected counts is 87.5 for all 4 of them. And you go to stat test, chi-square goodness of fit test, since this is goodness of fit. Your degree of freedom would be 3 because degree of freedom is number of categories minus 1. Since we have 4 categories, minus 1 is 3. So that's what you put. And then you should get your test statistic, which is around 1.06. And then it should also give your p-value, which is 0.786. And so when we have to show our work when doing these problems. So what I would do is you do the first one and the last one. So as you can see, I did it in black. And then in conclusion, since the p-value is really big, I would fail to reject the HO, and because p-value is greater than any alpha, and I do not have convincing evidence. Alright, next one is chi-square independence test. For this one, it's one sample but 2 categorical variables. For your null hypothesis, the 2 variables are independent. Alternative, the 2 variables are not independent. Plan, the name is chi-square independence test. Conditions are the same. Formula same, and then conclusion same. The only thing that's really changing within all 3 are the state. Yeah. Alright, so here's a example. So I highlighted the keywords in the problem. It says independent, and also says A random sample. A is an indicator of is singular, so that means one sample, which means independent. So in context, the state would be income, class, and gender are independent because those are that's the categorical variables. Alternative is the opposite. Plan or conditions are good. Alright, so now this one, the way you put in the calculator is different. You don't go to stat edit and put L1, L2. This time you have to go to your matrix. And at your matrix, you go to edit A and put all these numbers that you see here. These are the observed counts. So you put those numbers, and then after that, you go to stat test chi-square test. Don't go to chi-square goodness of fit, since this is not goodness of fit. Just go to the regular chi-square test. There, just press calculate, then go back to matrix and go to edit B. In that edit B, you will see your expected counts, and that's how you can see. That's how you can show your work. Like, because we have to like do the first one and last one. That's how you get those values. But then you can go back and do the same thing. Calculate, stat test, chi-square test, calculate, and then it should give you your test statistic and p-value. In this scenario, our test statistic is about 52.15, which is extremely high, so our p-value is going to be pretty much nothing. And then in conclusion, you're going to reject it because it's 0. P-value is less than any reasonable alpha, and you do have convincing evidence that H8 is true. This one. All right. Chi-squared homogeneity test, last one, or the third one. This one, you have 2 samples and 1 variable. Null hypothesis is that the categorical variable is the same in both samples, and for the alternative, the categorical variable is different in both samples. So those are some keywords there. Everything else is the same. All right, example. Keywords, it says are the same, that's an indicator, and also you take a random sample of 500 and 450. So those are 2 different samples. HO, income classes are distributed the same in both males and females. Income classes are distributed differently in both males and females. Everything is good and planned. For do, like for the calculus, the same thing as independence. You go to matrix, you input those values, and go to stat test, chi-squared test, find your, calculate, get your test statistic, go back to matrix to find your expected counts. P-value is 0 again, then the same thing as last time. All right, now we're on the next topic, which is least square regression line. All right, so everything about this has to do with the computer printout. And so we have this right now. And if you wanted to construct a LSRL, it would be, there's no like given y variable, so we'll assume it's awareness level just for this scenario. So we can say predicted awareness level, make sure to keep that, the hat, or say predicted, is equal to your y-intercept, which is 2.544, plus your slope 0.164 times your x, which is milligrams of caffeine. All right, now here we have all these interpretations that we need to do. All right, slope. For every additional milligram of caffeine, the level of awareness will increase by 0.164 points on average. Make sure to keep to have additional and on average in your statement. Interpret S, which is the standard deviation of residuals. Residual is y minus predicted y. So the average level of awareness differs from the predicted level of awareness by 1.532. So it's basically the average y differs from the predicted y by whatever S is. Then R, correlation coefficient. There's 3 things. It's either linear, nonlinear, positive or negative, or weak or strong. And so in this scenario, our correlation coefficient is 0.77. The reason you tell if the R is positive or negative is that you have to look at the slope. Since our slope is positive, that makes our R positive. R squared, it's blank percent of variation in Y is explained by the LSRL of X and Y. So then you just plug in your things for context. And lastly, y-intercept, which is also known as A. Basically, you're saying if the value of x is 0, the y is going to be this number. So if there is 0 milligrams of caffeine, I predict the level of awareness to be 2.544. Significance test. All right. So with this, we're dealing with beta, and beta is the population slope. So we're using our sample slope to predict the population slope. So our null hypothesis always is going to be beta is equal to 0, and then your alternative is either going to be beta is equal to not equal to 0, greater than 0, or less than 0. Okay, then after you do that, you have to state what B is. So where beta is the true LSRL between X, put that in context, and Y, put that in context. I'm using the same variables as last time. Plan, it's a t-test for beta, and then minor, do part is t is equal to b minus beta over SEB. Really, you don't even have to have beta because beta is equal to 0. So you just have b is over SEB. So the way you get these numbers is you look at the chart. B, as you see in orange, is 0.164, and then Standard error of B is in purple, 0.05. Divide that, you get 2.87. And then that's your test statistic, TCDF in the calculator. And then you get p-value of 0.007. But you have to look out for what the alternative says. Since this is two-sided, since it's like not equal to, you have to multiply by 2, and it should be 0.014. Forgot the extra 0. That's the p-value. But if it's say greater than or less than, you keep the 0.7. So watch out for what the alternative says. Conclusion, I'm pretty sure we all know how to do that. Okay, confidence interval. Let's say we're doing a 95% confidence interval for beta, where beta is the true LSRL between X and Y. A plan, T confidence interval for beta, the conditions are the same, linear. B plus or minus T star, T critical value times standard area of beta, of B. The way you get T critical value is from inverse T in your calculator. Since we're doing a 95, there is 0.025. So you put that as your area. In your degree of freedom, you do n minus 2, which will be 10 in this scenario since we put n is 12, df is 10. In red, I have the confidence interval. Conclusion, I have 95% confidence that the true LSRL between x and y of x and y is between those two numbers. Segmented bar graph is only if it's chi-squared independence or chi-squared homogeneity. Just make sure you read the equation to see whether it's a 2-sample or 1-sample or whatever it says. And so the way you do it, you look at the chart and you you divide by the total row value. So males, the entire row, there's 20 in total. So you do 5 divided by 20, 8 divided by 20, 2 divided by 20, 5 divided by 20. But then your females, there's 10 in that entire row. So you do 5 divided by 10, 3 divided by 10, 0 divided by 10, 2 divided by 10. And you convert those into a percent, which I did on the left. And then for your bar graph, you put the two variables at the bottom, which will be male and female. And then on the left side, it goes all the way to 1. And so then you're just adding your frequencies. So the cats are orange. And so for males, 25%, as you can see. And then the dogs are 40%. So 25 plus 40% is 65. So we'll put the blue marker all the way to 65. And then I did, the same thing for the others. Here's some other extra information that may be helpful. So degree of freedom. If it's a goodness of fit test, it's the number of categories minus 1. So if there's 4 categories, the degree of freedom is 3. Independence and homogeneity, it's row minus 1 times column minus 1. The graph is always skewed right, and pretty sure that's it. Yeah. So that's a really long review on this test, and hope everyone does good on it. See ya.